Hi everyone, welcome to our lecture today about signals. We are going to jump right into this. Inter-process communication. So, how do we connect our processes together? How can they communicate? And are there any simple ways to do it? Well, when a user process wants to contact the kernel, it's going to use a system call. So that would be you're writing a little program and you want it to do something like open a file or write data to a file. You would make a system call and ask the operating system to do that for you because your individual process doesn't have permissions to do that. But there are also certain times for when the kernel needs to talk back to your user process. And how does the kernel or our process talk to another user process? This is the field of inter-process communication, and it's what signals solve. It's what they are for. So these signals interrupt the flow of control. And the flow of control is that order, that top to bottom, following the recipe, the individual instructions that are all being executed line by line. So it stops that flow of control and jumps out to an explicitly given signal handler function. Now that can either be one of the default signal handlers that exists for that particular signal type, or it can be a specific signal handler that you have designated, that you've written by hand. So these signals, a critical point here is that they are telling your process to do something, that you need to take some event because something has happened. Either somebody is trying to notice or trying to notify your process about something, or something has occurred in the system that needs to be taken care of, or your process has done something bad and it needs to manage it. The set of signals is fixed. You can't send arbitrary signals from process to process. So the response and the meaning, the semantic meaning of the signals is going to be up to you. And there are even two signals that have no inherent meaning at all. They're just called user 1 and user 2. You assign meaning to them once you've caught them by making that signal do something. So maybe signal 1 or user 1 makes your process exit, and maybe process 2 or signal 2, user type 2 makes your process spawn a copy of itself. Whatever you want. Those are up to you. So some of the uses for these things. So in terms of notifications from the kernel, these are some typical reasons there. It could be because your process has done something wrong, something horribly wrong. It could be because of more mundane things, like a timer has expired and your process needs to be notified about it. It could be because a child process of your current process has completed executing. Maybe there was some event associated with the terminal, or some process on the other end of a communication link has gone away. So something that needs to interrupt your process about some occurrence that's happened. In process-to-process communication, some of the typical reasons for processes communicating would be to tell them to start and to stop. So to pause, to sleep, to do different things like that. They can start and stop each other depending on what needs to happen. They can tell each other to exit and to terminate. You could change modes in terms of their actions. You could change communication methods. So maybe we need to switch into a overriding method instead of an appending method, or maybe we need to switch to a different port than the one that we're on if we're using a network process, and they happen to be on the same machine. So let's look at some of these signals. We've got a couple different slides like this. This is the slide that talks about termination. So what's interesting is that most signals in Unix will kill your process, just about all of them. Even the ones that don't necessarily talk about killing the process, they'll still kill the process if they're not handled. But these are the ones that are specifically set aside to kill the process. So the headers here, this is going to be our signal name, or in terms of how we write it in code. The number here is also used in a few different places for when you're trying to get the type of signal that killed a process. We talked about that in a previous lecture. These are the individual numbers that map to the signals. And we have some easy English name for these particular signals. Catchable means that you can set your own signal handler to catch this signal and do something about it. You can alternatively set your process to ignore these signals, but only if this column here says yes. So notice, and as a sneak preview here, kill cannot be caught. Alright, so then the meaning of the signal, when it arrives, this will be what that meaning is. That's our center column here. The default action, if it's not caught, is pretty much terminate, 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 terminate. Everything dies. So that's going to be the case for practically all of these. Now, the core dump is an interesting concept we'll talk about later here, but the core dump is going to be a file that contains the detritus, the debris after a terminal is destroyed, or after a process is destroyed. So any process that outputs a core dump file is not going to clean anything up. So there's a host of different procedures that can run when you call exit. We've talked about that previously, about how it could be cleanup functions that are registered with @exit, that kind of thing, or memory that is explicitly freed. None of that happens if you are core dumping. It's just your process is terminating, and you get an explosion of clouds and gas and plasma, and you have to sift through it to see what's there. So anything that says core dump yes is gonna destroy itself. Anything that says no is a little more gentle in its cleanup and won't just immediately stop. It'll clean itself up, do all the proper things, and then terminate. So the abort signal, what that is going to do, this is sent by your process itself. So you call the abort function in your code itself. And what that'll do is it will send your own process the abort signal. So when that happens, then the abort signal arrives, and it won't do any cleanup. It'll just blow away your program. The quit one, this one is also sent by the user. It's not generated by abort. It's its own. It's the quit one. It can be sent from the terminal. It can be sent from inside the process. It can be sent from another process if they are controllable that way. But this one will kill off the process also. The interrupt one is a little more gentle. So interrupt won't cause a core dump, and it's more of a request to terminate. It gives your process a chance to clean things up. Incidentally, Control-C is going to send a sigint signal to the process that it's targeting and to all of the children of that process. For example, if you're at the shell and you've run some program, then you hit Control-C, it will send sigint to the entire process group, and that means your foreground process and any of the children that it has spawned. There's practically no difference between sigint and sigterm. They both have signal numbers, they both have different names, interrupt versus terminate, and pretty much the only difference I could find as I've been using them and as I've researched online is that sigint is the one that's sent out when you Control-C everything, and terminate is just another one that's available. Again, you can designate these to do different things, so if you want to add extra meaning, then you can certainly do that and write your own signal handlers. And finally, sigkill, at least here on this page, sigkill is the die, no questions asked, this process has to stop now. And it's not catchable. So what that means is that your process is never even notified about the signal. Okay? I'm going to say that again because it's an important, subtle point. Your process is never notified that it is about to be terminated. So when the kill signal arrives, the kernel simply removes your process. It's just gone. Your process never knows that it happened. It's just gone. It cannot be caught. You can register a signal handler for it, which will compile and seems to act like normal, except that signal handler will never trigger because it's never invoked. It's killed from outside the process. Okay, so we've looked at this particular bash command before. Kill is the typical way to send a particular signal to a particular process. So in our little example here, we are sending the terminate signal to process ID 1234. And we talked about some of the tricky options that are there. Well, let's try this thing. So here is a script and some usage of that script. So first, let's just print this thing out. So this is our sigterm test script, and what it's going to do is here it's going to say, hi, I'm a bash script, and then our next line registers a trap command, and this trap command is only going to execute if the sigterm signal gets received. And when that happens, what it will do is it will output sigterm is received, I'm exiting with a 0, and then semicolon to indicate a new command, exit 0. So it does exactly what it says on the label. It's going to kill itself off with exit 0. Then start a permanent loop here. This is as long as 1 is equal to 1. Then do the following and just spin here doing nothing. So send nothing, literally the text nothing, to the file dev null, which is like a black hole. It basically just doesn't do anything but spend time on the CPU. Then we're going to start this thing up in the background, a little ampersand there for the background. The job number is 1. This is the process ID, 1708. Then I'm going to run my psme command. And we talked about this one before. It's just a fancy PS. Here's the list of it in terms of what the long form of that PS command does. And it gives us this nice hierarchy of what's happening. We can see here my sigterm test is running, the state of this thing is running, and it's consuming 97.5% of the available attention of that CPU. Partially, that's because the CPU isn't doing too much else and doesn't really have to be bothered with very much else right now. And also it's because the way this is written is it really will do nothing else but run lines of code smoothly and evenly without system calls that block forever. So we can see that as one of the things that's being run. Note that the difference between the pluses here. The pluses show which ones are in my foreground process group. Since the sigterm test shell script was initiated in the background, it does not have a plus in it because it's not in my foreground process group. So if I send Control-C at the command line, it will not terminate the sigterm test script that's running. So there it is, running like crazy in the background, consuming a lot of CPU time. So I'm going to kill that thing off by sending the sigterm signal with the kill command to process ID 1708. We can see in the list here 1708 is the process ID, and the parent process of that is 1511, which makes sense because here's the bash shell that I'm running this in, and that's 1511. So away it goes, sigterm is sent, and we get the output text. Sigterm received, exiting with 0, and then it takes itself out. So all seems to be pretty clear. Let's look at some other signals here, some other common ones in our dictionary. The segmentation fault signal, we've certainly seen those before. That is in reference to invalid memory references, and it simply kills off your process with no recourse. It's not going to do any cleanup. You can catch this so that if the seg fault happens, it doesn't kill your process, but it instead keeps running. That might be an interesting thing to do for you. Your process might have garbage to deal with for the rest of its running, but at least you can stop it from actually terminating at that point. The sig bus is an interesting one. This means that you tried to reference a address of memory that does not exist. So you'd kind of have to work to make that happen, but if you tried, this is the type of error that you would get. The FPE error is a floating point error, and it's gonna this is most typically encountered when you divide by 0 or do some other impossible floating point or integer operation. So they're not all that common, but the typical reason is you divided by 0. Sig-ill is also very rare. This is going to be sent for when your process is sending a CPU instruction to the CPU that doesn't exist. So it's malformed, it's bugged, it's got problems. You don't have permissions to send that CPU instruction. So again, that's a really hard one to send. But if you figure out a way to do it, this is the kind of instruction the signal you'll get back. System calls, kind of in the same vein. This is sent when a system call is being passed an incompatible argument. For the most part, we're using libraries that are going to be managing our system calls, so it's really unlikely you'd get a sigsys error. So both of these are pretty rare these days, unless you're doing driver development or kernel development. You probably aren't going to see these. A pipe error is a little more common. This is going to be when a process is trying to write into a pipe, and we're going to talk about that in an upcoming lecture. But when your process tries to write to a pipe, but the other end of the pipe, there's nobody there. So it's like you pick up the phone and start talking, but nobody's listening on the other end. You'll get a signal about it. And yes, the default is kill off your process, and that's the case for all of these. All of these are terminate, core dump all over the place, don't do anything clean, just destroy yourself. So why would we care to notify about these events? Well, this allows us to provide some branching logic to our programs. We can do things like perform final file writes, so maybe finish off a log file, indicate that something is happening in that log file, and then terminate. Maybe it gives us a chance to free up a bunch of memory that we want to explicitly manage. Finishing up log files, like I said, and maybe we want to send different signals to ourselves or send different signals to other processes because of what we've received. So when a process is catching a signal, and again, catch just means that you register some signal handler for that signal, and that signal handler can be one that you write or just take the default action. So when you're catching it, you can choose to do all of these or none of them or some of them, whatever you want. And then after you've done that, that signal, once it's caught, is not going to continue. It won't do its default action unless you said do the default action. If you have it target one of your own signal handler functions, that signal is gone. You can still, though, after you do these things, terminate your process if you like. And that's usually a good idea. So if you're receiving sigints and sigterms and sigquits, maybe ignoring them and writing to the log file isn't the best. Maybe you really should terminate your process. Okay, so let's look at some of the control signals that exist. So the alarm signal, this is sent specifically by the alarm function. So it's a way to register something in the future, like notify my process 5 minutes in the future, go. And then you'll receive this alarm in the future. Incidentally, again, that alarm is going to kill you. It's like your alarm clock is hooked up to a bomb. It turns out that it destroys your process also. The stop signal is again in that same vein of signals that cannot be caught. So this one and sigkill, these cannot be caught. There's no choice. This is going to stop execution. In the same way, when you're at the keyboard and the shell and you hit Control-Z and it stops your process, that's the kind of stop we're talking about. This one cannot actually be caught. Now, the one that is sent when you hit Control-Z on your keyboard is actually sig TSTP, terminal stop. So that one is the one that's mapped to Control-Z on your keyboard. If you want to send a sig stop, you'd have to manually do that with the kill command in bash. But as you can see, it's a much more powerful command. It can't be caught. The continue signal is used to start something back up again. So when you resume a process, like with FG or BG, and start them back up running again, that will begin them running with the sigcont signal. And the default action for this one is, one of the rare don't die actions, because the whole point of this one is to say start running again. All right, the hang up signal. This one has its history, its origins when we were using dial-up modems to connect computers together. So a dial-up modem is typically done through a phone connection. So that phone connection is established, and when the user hangs up, you get a specific signal about that. So that is going to happen when the terminal is terminating. So like you disconnect, you actually kill off putty, say, or you close down your terminal window without telling the process that that it needed to stop. You can generate sighup signals that way sent to all your processes. And again, it's going to terminate everything by default. So you have to be a little explicit if you want your processes to survive a hang-up. Trap is kind of a custom purpose one. It's going to be sent when you are trying to do debugging, so you can register your function to watch for trap signals. And this is unrelated to the bash trap command. This is a way to say we have various, if there are functions that are happening or values that are changing in our variables, we can have those things trigger events that tell our process to stop. This is one of the ways that GDB works. It's going to use the trap signal to control itself. And again, the default action is if you don't manage that, terminate the process and blow up all over the place. Alright, so timers. If you want to wait a specified period of time, you can do a busy wait, which is going to consume your CPU continuously, and it won't necessarily accomplish anything. Or you can tell the kernel that you want to be notified after a certain amount of time has passed by. So to set that timer in Unix, what you would do is call the alarm or the uAlarm functions. And I think U here is, I think it's micro alarm. I think it's like less than a second, while alarm deals just in seconds, something like that. After the time that you specify has passed, the kernel will send your process a sigalarm signal, and then you can deal with that at the time. This is actually how sleep works. So sleep is going to call alarm, and after that's been done, so that'll register, say, sleep 5 seconds into the future. Then sleep, the function, is going to call pause, which stalls your process, and it puts it into a waiting state where it won't do anything else. And we'll talk more about pause in a moment, but one of the things that it does do is it allows it to still receive signals, even though it's sleeping, which that sleeping state normally wouldn't do. But because you used pause here, then it puts us into a waiting state. When that sigalarm signal arrives, sleep returns and the process continues. So that's what that's for. Yeah, and yes, that uAlarm function really does deal with microseconds instead of seconds, like alarm does. All right, so another entry here in our dictionary, the sigchild signal, which is a very important one. This one doesn't have a number, but it's about when a child process terminates. It's certainly catchable, and the intention here, the meaning, is that a foreground or a background child process of the process that's received the signal has terminated, has stopped, or has continued. So something has happened to that child. There's no default action if you don't catch it, so this is one of the few where nothing actually happens at all. It's up to you to manage it if you want. There's no core dump associated with it, of course. So normally, wait and wait PID are going to suspend a process until one of the child processes has terminated. So by using this signal, this allows that parent process to do something else instead of just going to sleep and being notified. So let me rephrase that. When we are running our process and we call wait, that causes our process to block, or we call wait PID. That is going to suspend our process entirely until one of the child processes is terminated. However, instead of doing that, we can continue to run our program and use a signal handler that is listening for the sigchild signal. And when that signal arrives, that signal can be used in our process to do what we want with it. So maybe we just wait for notification of child termination instead of blocking until child termination. So do whatever you want until it arrives, and when it arrives, deal with it then. So we could then decide to immediately call wait or wait PID on what just arrived, or maybe we leave that child a zombie for a little while and finish up what we're doing and then go back and call wait. So here are the two user 1 and user 2 signals that we talked about at the beginning. They don't have any particular meaning. They are catchable, and note that in both cases they still kill off your process. So you can assign these to whatever you want. It's up to the author for the sending and the author of the receiving process to agree on what they mean. Otherwise, you'll receive processes that don't agree. Maybe you meant spawn a copy and the receiver instead dies. So it's up to you to designate what they mean. Alright, let's try this out. So here we have our script, cat sigchild test, and this one's a little bit more complicated than our previous one. Here we have hi, I'm a bash script, that's what this line says. Set-m enables job control, which is going to enable us to send back and forth this sigchild signal. And then we're going to register a couple of different traps. So one of them is for the signal user 1, and one of them is for the signal CHLD. This is child. So you can omit with the trap command. You can omit the sig in front of these things if you like. It's kind of a tradition to do it this way. You can also spell it out the full way. Either way works. So register a trap for both of those signal types, and then go into an infinite loop doing nothing. So what's going to matter is obviously what's inside these traps. So the first one, if we receive a user 1, this says triggering a child process termination with a silent ls. That silent ls looks like this. Here we have ls, but the output of that ls goes to dev null. Now, when that ls is launched by our shell, by the one that is being initiated by our shell script, this ls is put into its own shell, its subshell of this process. So the ls gets its own, the ls terminates, and when it terminates, that is going to cause a sigchild to bubble back up from that terminating process and be sent here to our script. When that occurs, the second trap is going to be invoked, and that is going to say sigchild has been received and it's exiting. So these two are working in tandem. Okay, so here let's run this thing and put it in the background. That's again going to stuff this right into our CPU with job number 1, and it's in the background. If we look at the PSMe listing here, we can see that the runnable state for our sigchild test is consuming 102% of the CPU. So we're pulling in processing power from neighboring computers here. No, it just means that on some average cycle, its numbers didn't quite add up. But because the percent CPU column never does, it's kind of a time average thing. And it's saying that we are certainly consuming all the CPU power on this machine, which means nothing else was happening on this machine at the time. Then we're going to send the SIG_user_1 signal to this process, to our shell script. Here we indicate the actual process ID for it. Then we get back in results the triggering a child process termination with a silent ls. So remember, SIG_user_1 has been caught. So it's been caught by this trap statement, which means the user1 signal won't do anything else itself to our shell script process. However, because of the silent ls that runs, the ls terminates, sends a SIG_child backup, and we see the output here of that. The SIG_child is received and it exits. And here we can see that it exits itself right there. So that seemed to work just fine. We can use a PSME afterwards and see that SIG_child test script has in fact terminated. So that looks good. So if we do have some sort of abnormal termination, and we mentioned that there are these core dump files that are generated. So these can occur during runtime if the process crashes because of some seg fault or the bus error or whatever they are. And when that happens, the memory core dump file that's created is going to contain the contents of all of the variables, all of the hardware registers like on the CPU, and even some additional information like what the kernel thought about that process in terms of what it was registering and the pointers it was using to keep track of things. It will give you all that information whenever that abnormal termination actually occurred. So all that will be baked into a file. Then you can use that core file to identify what happened if you're able to read it. They're actually pretty obtuse. They're not well designed in terms of being human readable, so actually understanding them can be a little hard. And depending on configuration, for example, some of our OSU servers, actually finding those core dump files is next to impossible. So don't count on actually being able to discover these things on a big giant shared machine, because they take up a lot of space when a process terminates. The intention is that they don't stick around. So if you have your own machine, you can configure it to save those, say, into a temp directory or a core file directory, something like that, so you can keep a hold of them. So where does this term core come from? Well, I want to go through a couple of paragraphs here from Wikipedia that are very well written about this. So the magnetic core memory was the predominant form of RAM for 20 years between 55 and 75. So we've had memory for that long. We've had computer memory, random access memory, since the 50s. And this memory is often just called core memory or informally just core. And core memory uses these tiny magnetic toroids, which are essentially tiny, tiny magnetic rings. And these cores, through which wires are threaded to write and read information. Each of these cores, these magnetic rings, represents 1 bit. And the core can be magnetized in 2 different directions, either clockwise or counterclockwise. And the bit stored in that core is either 0 or 1, depending on that direction. The wires are arranged to allow for an individual core to be set to either a 1 or a 0, and for its magnetization to be changed by sending appropriate electric current pulses through selected wires. The process of reading the core memory causes the core to be reset to a 0, which erases it. And this is called destructive readout. When not being read or written, the core maintains the last value that they had even when the power is turned off. So this is non-volatile memory. So that's pretty intense, that the act of reading memory back out destroys the actual core that you're using. So if you want to keep a copy of that bit of memory, you have to read it and then kind of fork out the result of it. So write it back into a separate bit and take the other bit somewhere else for your use. So these things are gorgeous in look. So take a look at this thing. Here is a nice zoom-in view of one of these core memory modules. So using smaller cores and wires, the memory density of core slowly increased. And by the late 1960s, a density of about 32 kilobits per cubic foot was typical. 32,000 bits per cubic foot. However, reaching this density required extremely careful manufacture, almost always carried out by hand, in spite of repeated major efforts to automate the process. And look at these things. Look how fine these little tiny rings inside here are, and all the little wires that had to be stitched through by hand, and all these guy wires holding them all up. Perfectly organized, perfectly spaced. This looks like fabric that's been stitched, machine stitched, and then on the outside hand soldered onto all the rest of these terminal pins. It's just gorgeous. It's very pretty. So the cost declined over this period from about $1 per bit to about 1 cent per bit. And the introduction of our semiconductor memory SRAM chips in the 60s is finally what started to sound the death knell for the core memory market. So our first successful DRAM chips, the Intel 1103, arrived in 1972 in quantity, and those were all the way at 1 cent per bit. But the process accelerated so fast, DRAM went crazy, prices went down, capacities went up, and just even a few years later, Core was done. It was off the market. So this thing is a fascinating little insight into history for where computers really were assembled by hand. Even the memory was. So my laptop has 16 gigabytes of RAM. So at this price, that'd be about $16 billion for my laptop. And when the prices went down, then it means my laptop would have only cost $160 million. So your money at work, right? Your government money at work when they buy all these big computers. So signal handling API. So signals that hit your process are going to cause the default action to occur. And those default actions we spell out in those signal dictionaries earlier. Now we're going to talk about the API that actually manages the actions that can happen. So in order to modify that default action, we're going to organize all the signals that it could arrive into sets. And when we have a set of these signals organized, we can assign whatever our own custom defined signal handler is to that set, and that'll allow us to override the default action. So before we can talk about that, let's look at a few utility functions that enables this all to work. So first of all, pause. So we talked a little bit about this before, but sometimes a process has nothing to do, and you consider that you might call sleep on it. Sleep is handy, but it's a blocking system call, and it means that your process goes away and never comes back. And if we do something like that, the never comes back only finally finishes when time has expired and our process resumes execution. But if we want that to be able to respond to signals, we can't just call a raw sleep. And to do this, we can call the pause function. So if a signal is going to be ignored, then the pause continues to be in effect. So imagine that we call pause. So that means that if a signal is set to be ignored, then pause doesn't do anything. The signal doesn't hit our process. If a signal causes our process to terminate, then that pause that we called also doesn't do anything because the process has died. However, if our slumbering process that we called pause on, if it does catch a signal, because pause enables all the signal handlers, then the appropriate signal handler function gets called. And after it's done, the pause function returns and resumes execution at that point. It returns a -1, and the error no variable, which is part of the standard input-output library, that variable, which is always available in standard input-output, is set to the EINTR flag, or that value, so you can check it to see what happened. In this case, it's saying, hey, it was interrupted. And then, for example, you could just immediately issue a pause again. So if a signal arrived that you didn't care about, you could just go back to pseudo-sleep with pause. Whereas if you did care about it, you could do whatever you want from then on. You could have your process, maybe it goes and terminates, or maybe it spawns a copy of itself. Who knows? If you want to send a signal to yourself, you can use the raise function. This is kind of analogous to in Java, where you can send signals to your processes. You can raise alerts and issues. You can do the same thing in C. You use raise, and you give it simply the signal number that you want to send. So the alarm function sends your process a sig-alarm signal at a later time. And we've seen this already. So the signature for this function is unsigned int, that's what it returns, and you give it an alarm. And you pass in the number of seconds that you are going to want this alarm to come back to you after. So alarm returns immediately, unlike sleep. So while sleep doesn't return until the time has expired, alarm returns immediately and lets your process continue. Then you have to manage the sig-alarm signal that arrives. If you don't, it'll terminate your process. And you can only have one of these alarms registered at any given moment. Okay, so how do we organize the signal sets? So signal sets are a special type, and it's sigset_t. They're defined in the signal.h header library. Some of the functions that we'll use for managing these things are going to be empty, fill, add, and delete. So let's look at these: seg, empty, set, and on. So to declare one of these things, we just say sigset_t, and then the name that we want to use here. It's my_signal_set. To initialize or blank these things out, then you use the sig_empty_set function. Pass it in the address for your variable. To initialize this thing or to reset it such that the set contains all signal types, then you use fillset. To add a specific single signal type, you'd use addset, sig_addset. So this one, you're giving it the address to your variable and then the signal number for what you're trying to register. And to remove one, it's the same thing. You're using sig_delset, and you're giving it the signal that you want it to remove from that set, like sigint. So how do we actually use these signal sets? So those are used in the sigaction function. So the sigaction function is going to register a signal handling function that you've created for a specified set of signals. So here's the function signature for sigaction. The first one, signo, is going to be the signal type of interest that you are registering with this function. So remember, this function is what creates or what registers the signal to a particular signal handler. So the first one is that signal. So this is the sigaction call for sigint, and then we call another one for a separate sigaction call for sighup. So one for each. So then the second parameter is going to be a pointer to a data-filled sigaction struct, which is different than the sigaction function. A pointer to a data-filled sigaction struct, which is going to describe the action that we're going to take when the receipt of that signal has occurred. And then the third one is going to be a pointer to another one of these sigaction structs, which the sigaction function is going to use to write out what the handling settings for the signal were before the change was requested. And the reason for that is you could imagine that your process, your signal handling function, actually modifies what the behavior is for this signal once it's received. You can remember what your original one was, so perhaps you could revert back to it later by using this original action parameter. Alright, so let's look at the sigaction structure. So these are the things that are loaded in as arguments to the sigaction function. They have the same name, which is kind of confusing. So you got to pay attention in terms of, are we using the function or are we using the struct? So here is the struct, and it has 4 different variables. Our first variable here is the SA handler variable, and it's going to be set to one of 3 different values. First of all is sig_dfl. That is, take the default action for this signal. And that's actually the one, you can pretend like this has been set for all signals at the very beginning of your process. That's just the default. This has already been set. And you don't use a particular explicit signal handler function for that, because you're saying take the default action at nothing special. And remember, default action is usually terminate. Alright, signal ignore. This is ignore the signal. You can use this one to tell your process to simply ignore that signal as if it never occurred. And then finally, the other option you could set SA handler to is a pointer to a function that should be called when the signal is received. Okay, so we're talking about a particular C language feature, which is function pointers. So let's look at function pointers. They look kind of complicated, but they're not that bad. In a signal handler structure, we are defining one of these, or we're indicating that we need a pointer to a function in this line here where we say SA handler. So the little asterisk up here in front isn't really a dereference notification. It's the void out here in front and the arrangement of the parentheses and this data type over here that is telling us that this is a pointer to a function. So the void indicates that this particular signal handling function doesn't return anything. And the int, out in the front here in parentheses, is indicating that it's pointing to a function that does have a parameter. So SA handler, whatever you put into here, it needs to take a parameter, and that has to be an integer. This integer is going to hold the signal number when the signal handler was actually called. And that's important because you could register multiple signals with this struct that we're filling out here. So the only way to tell which signal caused this handler to start is because that will be written into this int. And we'll explain that here in a little bit. So here's an example of a function pointer. So we have a function called add1, and this add1 function is declared to say it's going to return an integer, and it receives an integer as its input. So here we can see input arg is the name of this thing. That's just our declaration for the function. So then we're going to start our main function, and in here we can see that we're going to create a function pointer here called fparg. That's our function pointer argument, and it takes an integer. That's what this argument here, or this parameter name in parentheses, means, and the little arrows here show that this is the same as the integer that's absorbed by add1. And then the int on the far left here of our fparg statement is telling us that these things return the same thing, an integer. And I set this equal to the name without the parentheses for the function that I am assigning, or the pointer to the function that I am assigning to this function pointer. And then down here we actually specify the guts of the add1 function. This one, we are saying all it does is take the input and add 1 to it, so nothing's particularly strange. So here's int input, and here's return that back out. Alright, getting back to our sigaction struct here, let's look at the second parameter, the SA mask parameter. This is going to indicate which signals should be blocked while that signal handler is actually executing. So blocked in this case means that the signals arriving during the execution of SA handler are held until the signal handler is done executing. And at that point, the signals are then all delivered in order to your process. So it doesn't really block them and permanently trash the signals that arrive. What it does is it says, just hang on, wait for a minute while this signal handler function runs, and when it's done, then all those signals are allowed to hit your process in order. And one note here, that multiple signals that arrive of the same type could be combined. So if you receive multiple sig childs in a row, those could all be combined into one sig child. So you can't use this to count signals, because you don't actually know how many signals of that type arrived. It could be 1 to who knows how many. And for this particular parameter, you're going to pass in one of those signal sets that we built up earlier. So you're going to indicate which signals as a set should be blocked, which is held until the end of execution with this argument. Our SA flags parameter, this is the third one. This has a few different options you can put in it. These are just the standard option flags that we've seen in so many other functions. Some interesting ones here, rest hand, SA_rest hand. This is going to reset the signal handler back to the default action after the first signal has been received and handled. So it's a way to take a different approach the first time something arrives, and then reset back to the default action after that first one has been received. Another interesting flag is the siginfo flag, and what this does is it's going to tell your kernel to, instead of using SA handler for its function pointer, to instead use this bottom one, which is SA_sigaction. So again, a third use of the term sigaction. In this case, it's a parameter of the sigaction struct itself, which is used by the sigaction function. So this one says, when you set siginfo, you're saying don't use signal handler, instead use sigaction as the function pointer. And the difference here is that this particular one has more options available to it, as you can see from the arguments here, and we'll talk about it here in just a second. And you would just set this to 0 if you don't have any, which is the common setting. So some of these options for that fourth attribute, so you can set the alternative signal handler inside here. It allows us to pass in a struct, and this is a siginfo t struct. Oh, this is you pass in a pointer to the siginfo t struct, which is going to be written to once the SA_sigaction registered signal handler executes. And the struct that's being written into is going to contain information about, for example, which process sent you the signal. So that's pretty handy if you want to know which process, like by process ID, actually sent that sigterm signal, so you can punish it back. You could get that out of this particular struct once it's been written. The last argument is one of those do not use deprecated arguments. This is from an old thing called a context, which is a very obscure, very obsolete, very non-POSIX way to manage user threads that essentially let you reset the entire state of the CPU. Horribly non-reentrant, very interesting stuff, but we just don't use it. It's not needed anymore. Most of the time, you're not going to use this lower option. You're going to use SA handler instead. It's simpler. Okay, so let's look at an example for this thing. So we have our program called catchingsignals.c. Here's the user or the libraries that we're going to add for this particular thing. We have two functions of interest here. First one is called catchSigInt, and the second one is catchSigUser2. Note that they both take an integer, which contains the signal number for what triggered this particular signal, or for this particular function. So the top one we're going to use for SIGINT, and the bottom one we're going to use for SIGUser2, but nothing about the declarations or instantiations about these functions here actually indicates that. So you don't register this function in the body of this function. That's done elsewhere. We're just defining what the function does at this point. So inside the SIGINT one, for example, it is going to, we've got a string literal defined here, which is called message, and it's simply saying that we caught SIGINT and we're sleeping for 5 seconds. And then we use the write function to write to standard out to pass in that message and manually have to indicate 38 bytes. And we can't use printf here. This is the first time reentrancy really matters to us. So we can't use printf because printf is non-reentrant, which means that the usage of standard input-output function calls can be hazardous. The values of those calls, all the buffering that's being done, all that data can be trashed as these signal handler functions go back and forth. So you can't use those. So instead we're going to use write, because that's a safe function. Even though it's very basic, we can use that in place of printf. So we can't use string length, which is where, we'd love to say string length of message and put that in here, but that's also non-reentrant, so you have to manually count it out. Then I'm going to send myself SIGUser2 and then go to sleep. So one thing that you might notice about this is that this seems like we're creating a race condition. We're raising a signal, and then we're calling sleep. If we'd wanted to wait 5 seconds and then call SIGUser2, then maybe we should have reversed the order here, right? So we're going to leave that mystery hanging for a moment. So this is going to send SIGUser2, and if it happens to be blocked for some reason, then the signal will only arrive after that block is completed. Okay, so now let's look at SIGUser2 as our other function. This one simply says to output to the user that SIGUser2 was caught, and that then it exits. So that's all it does. This one just kills things off. User2 kills it. SIGINT is going to raise a SIGUser2 and sleep for 5 seconds. On this page, we can see the rest of the guts that declare the signal sets that set up the sigaction functions to actually run. And we'll look at the results here in a second. So first of all, we're going to define 3 separate sigaction structs, and they are called the one for SIGINT, SIGINT_action, the one for SIGUser2 action, and the last one, ignore action. And note that we can completely initialize this really complicated struct. We can completely initialize it to all be empty by just using curly brace 0. That kind of wipes the whole thing out. All right, so then let's use the SIGINT action struct that we've defined. Or let's define all the member variables of this struct. So first of all, we are going to look at the SA handler member variable, and we're going to set this equal to our this function pointer. We're going to say equal to our catchSigInt function. Then we're going to fill in the entire mask member variable for this SIGINT for the sigaction structure. So what that does is it says we're registering all signal types such that none of them are allowed to interrupt with the processing of the SIGINT signal. And we're saying no flags. For the SIGUser2 function, we are setting up a sigaction struct, and in this particular one we're saying we're registering this thing for the catchSIGUser2 function, and we are filling it up again with all functions, or all signal types. So we're saying no signals are going to be allowed to interfere with the running of any signal that uses this struct. So note again that we still haven't actually registered a particular signal to do anything. All we've done is set up some sigaction structs that we could use later. And then finally, we're going to set up our last sigaction struct, this ignore_action one. We're going to set this thing, its signal handler, up to simply be sig_ignore. And that's all you have to do. If all you intend to do is to set things up to be ignored, to set signals up to be ignored, you just have to use the sig_ignore flag in sahandler. Now, the next 5 calls actually register these things. So the top one is going to register sigint to do whatever is in the sigint action sigaction struct. Okay? So that's a lot of words that are all very synonymous and use the same letters and pronunciation. So let's see it again. Let's say it again. This particular statement is saying the sigaction function runs, and it is going to establish for the sigint signal only when it's received by this process to do whatever is contained inside the sigint_action sigaction struct. Okay? And no particular flags otherwise for this thing. And this would be the one where you'd like copy back out the thing that was originally in here. We don't really care. We're just setting it here, setting and going. We do the same thing for sig_user2. For that particular signal type, we're setting the sigaction struct that we've previously built for it. And then for the next 3, sig_term, sig_hup, and sig_quit, we are setting these all to be ignored by registering those signals with this particular sigaction struct. Remember, this is our ignore one that we've set up, and I've color-coded them so you can a little more easily tell what's going on. We're just simply saying term, hup, and quit aren't going to be able to do anything. All right, then we send out some stuff to the user. So printf, sig_term, sig_up, and sig_quit are all disabled. So tell the user what you and I as the programmers already know. Those signals aren't going to do anything. Then we tell the user to send a sig_user2 signal to kill the program. And then send a sigint signal to sleep 5 seconds, and then kill this program. So then it fires up a while pause. So remember that pause is going to put our process here to sleep so that it doesn't consume CPU time, but it will wake up to signals that arrive. So let's go back and look at those signals here for a second. Now that we know that during a sigint or a sig_user2, that no signals are going to be allowed in to mess with our program flow while those things are being processed. And we can see that again because sig_fill_set was used here for sa_mask for both catch sigint and catch sig_user2. Let's go back and look at the implementation here. So for catch sigint, as soon as this code starts, no signals are allowed in. They're all queued up and they'll all wait for us. So when we say raise sig_user2, the sig_user2 signal is put up in the queue and stays there and can't do anything. Then we sleep for 5 seconds, and that's just stalling everything out. And while this is running, remember, sig_user2 cannot hit. Finally, after the sleep finishes and this function returns, sig_user2 is delivered to our process. And when sig_user2 is delivered to the process, it invokes this particular function, which tells the user that it caught the sig_user2 signal and that it is exiting, and then it calls exit. So that is the mystery solved for why we would go raise in front of sleep. Well, let's now, and of course we could have done this in either order. We've simply done it in this one to show the effect here. Let's look at the actual results of running this. Here is our program catching signals that we looked at before, and at the beginning it tells us that it has disabled all those signal types. It informs the user how to kill it off, either with sig_user2 immediately or sig_int that takes 5 seconds to do it. Then let's look at what happens when we send a control-C. What that does, because this thing was in an infinite loop, is it sends a sig_int to our process. And as we saw before, as we talked about before, that's going to make this thing send itself a sig_user2 and then sleep for 5 seconds. So that catches sig_user2 and then exits when it's finally processed. So in another try, let's put this thing in the background now. So this thing goes back to the background, the little prompt is written out here even before, so we have access to start typing at this point, and then that other process in the background starts outputting text still. So it's telling us all the different instructions that we need. And I hit return a couple of times here just to give myself some space, some breathing room to see what I'm doing. Then I can say kill sigterm and then pass in the particular process ID, 29443, and that won't do anything because it's been disabled. Sigterm doesn't do anything. Then I can send in siguser2, which is the one that immediately kills it, and I'm immediately rewarded with this process terminating. So instead of getting a notification that it's sleeping for 5 seconds and then dying, it simply just dies right there. Okay, so child processes and inheritance. When you are calling fork, the child processes are going to inherit and get their own instance of the signal handler functions declared in that parent. These are going to be assigned to the same signals as the parent automatically. So a child process that you've created has the same signal handler functions that you've previously defined. So that could be good, that could be bad, depends on what you're doing. So be aware that they're all going to be inherited. But here's something interesting. If you call exec in your process, it will remove any special signal handler function that you've wrote and that you then assigned to SA handler or SA underscore sigaction. That means that the only ways to tell a child process that's going to call exec to do anything meaningful are with sig default and sig ignore. So another way to say this is, and I've written this down word for word because it's a really critical point, sig underscore default and sig underscore ignore are preserved through an exec. This is the only way to tell processes that you use the exec functions on that you didn't write, like ls or other bash commands, that they should ignore a particular signal. In other words, there is no way to set up an arbitrary signal handler for programs you can't change. You can only tell programs that you haven't written, that you can't alter their code on. The only thing you can tell them is to ignore specific signals, because obviously telling them to do the default action is just a way to get them all quickly killed. So the only other thing you can do is you can set them to ignore signals, and that's about all you can control when you exec things. But fascinatingly enough, this turns out to be a critical point for our shell writing program. Okay, we can also block signals. So not just in terms of during a signal handler, we can block them from execution at any time in our program. So, and again, being blocked just means that they're delayed until until we unblock them, and then they're all delivered in a big mass. This could be important if we have some special block of code that we really don't want to get interrupted by a signal. And you would do this with the sigprocmask function. Not particularly common, I don't have any examples of it here, but just be aware that signal handler functions aren't the only place where you can mess around with functions. You can ignore them with sigprocmask. And for our last slide here, let's talk about signals and system calls. So signals can arrive anytime, even in the middle of a system call. So like if you say, read some 1 gigabyte file off the hard drive, you could get a signal during that. The system calls are pretty good about preventing data loss when that happens, from preventing corruption from messing up all the buffers, and they can also prevent partial actions from happening. So normally, system calls are going to return an error if a signal interrupts them, and they'll set errno to that standard EINTR value. They're pretty good about not corrupting things. They just stop and they let you know what happens. System calls return with an error. And you can tell them then to automatically restart by setting a particular flag inside that flag's variable that we talked about earlier in the sigaction struct. Alright, well, I hope that was useful for you. There's a lot of information in here about signals that is of use in lots of different places in systems programming and operating systems programming, and I find it's really, really useful and especially handy for our shell writing program. Alright, if you have any questions, we will see you on the discussion boards. Thanks!